The universe is a canvas of breathtaking beauty, where stars burn brilliantly for eons, shaping the cosmos with their light and heat. Yet, all things possess both a beginning and an inevitable conclusion. Every star and every galaxy, regardless of its former majesty, is destined to dim. As they reach the end of their life cycles, their radiance is extinguished, leaving behind cosmic graveyards scattered throughout the void, silent monuments to the passage of time and the unavoidable decay of stellar giants. This raises a profound question: can life survive in a universe that is slowly exhausting its energy, and what does this mean for the future of everything we know? Our journey takes us through these galactic cemeteries to listen to the final, whispered stories of the universe's last remnants. Stars are born in the cold, vast reaches of deep space, where immense clouds of gas and dust churn in the darkness. These nebulae, spanning millions of light years, may appear serene, but they harbor the potential for incredible transformation. The birth of a star begins when a specific region within one of these clouds starts to collapse under its own gravity. As the particles of gas and dust are drawn together, they begin to heat up, packing tighter and tighter over time. Initially, the gas might cool and disperse, but as gravity pulls the particles into a smaller volume, the temperature rises sharply through the process of gravitational contraction. When the accumulated mass becomes sufficient, the pressure at the center becomes extreme, reaching millions of degrees. This hot, dense core is known as a protostar. While not yet a true star, it is the precursor to a massive energy furnace. At this stage, the protostar radiates significant energy, though this power comes from gravitational collapse rather than nuclear fusion. Meanwhile, the surrounding material flattens into a rotating disk, which will eventually coalesce into planets and moons. A critical turning point occurs when the internal temperature and pressure rise high enough to ignite nuclear fusion. In this process, the most abundant element in the universe, hydrogen, is forcibly fused into helium, releasing staggering amounts of energy. This marks the true birth of a star. The energy from fusion provides the outward pressure necessary to counteract the inward pull of gravity, creating a delicate state of equilibrium known as hydrostatic balance. As long as this balance is maintained, the star shines steadily, radiating energy across the spectrum. The interior becomes a stable core of fusion, while the outer layers of plasma and gas radiate heat and light, giving the star its characteristic brilliance. The ultimate fate of a star is dictated by its initial mass. Smaller stars, like our Sun, spend billions of years calmly burning hydrogen. In contrast, massive stars consume their fuel at an incredible rate, racing toward the end of their lives. For these giants, the conclusion is often violent and spectacular, ending in a supernova explosion or collapsing into a black hole. Meanwhile, lower mass stars undergo a gentler transition, shedding their outer layers to leave behind a white dwarf. During these formative stages, powerful stellar winds and radiation pressure clear the surrounding space of leftover debris, a process called photoevaporation, allowing the newborn star to shine clearly and begin its long tenure on the main sequence. As a star ages and exhausts its hydrogen fuel, it must find new ways to sustain itself. For a star like our Sun, the core will eventually shrink and heat up, causing the outer layers to expand into a red giant. Eventually, it will shed these layers, leaving only a dense, cooling core, the white dwarf. For more massive stars, the process is far more intense. They burn through heavier and heavier elements in layers, much like an onion, until they attempt to fuse iron. Because the fusion of iron does not release energy, the star loses its internal support and suffers a catastrophic collapse. The resulting supernova can momentarily outshine an entire galaxy, scattering heavy elements, the building blocks of planets and life, into the interstellar medium. What remains after such a cataclysm depends on the leftover mass. It may be a neutron star, an object so dense that a small fragment would weigh billions of tons, or it may collapse further into a black hole. A black hole is a singularity in space-time where gravity is so intense that not even light can escape. Its boundary, the event horizon, marks the point of no return. While black holes are invisible, we detect them by their influence on nearby matter, which forms an accretion disk that heats up and emits detectable radiation as it spirals inward. These events are not just endings. The shock waves from supernovae can compress nearby gas clouds, triggering the birth of a new generation of stars and continuing the cosmic cycle. Lower mass stars end their journeys more quietly. Without the pressure to fuse elements heavier than helium, they become white dwarfs, hot, dense remnants about the size of Earth but with the mass of a star. Over trillions of years, these remnants will slowly cool until they no longer emit light, becoming hypothetical black dwarfs. However, the universe is currently too young for any black dwarfs to exist yet. These quiet endings still contribute to the cosmos, as the material ejected during the red giant phase enriches the galaxy with carbon and oxygen. Galaxies, too, are not eternal. They are vast systems of stars, gas, dust, and dark matter that grow, collide, and eventually fade. Born from small fluctuations in the early universe, galaxies evolved from irregular clusters of young stars into the magnificent spirals and giant ellipticals we see today. Throughout their history, the cycle of stellar birth and death drives their chemical evolution. As the gas is consumed and the stars dim, galaxies eventually lose their ability to create new life, slowly transitioning into a state of quiet dormancy. This grand narrative of birth, evolution, and eventual decay defines the very structure of our universe, a story written in light and shadow across the vastness of time. Elliptical galaxies often represent the elder statesmen of the cosmos, populated primarily by ancient stars and nearly devoid of the cold gas necessary to birth new stellar generations. In stark contrast, irregular galaxies defy neat classification, their chaotic forms shaped by violent collisions and intense gravitational encounters. The universe is a mosaic of these diverse morphologies, each reflecting a specific stage in the grand narrative of galactic evolution. At the heart of this evolution lie the processes of collision and merger. While individual stars within a galaxy are separated by such vast distances that they rarely collide, galaxies themselves are frequently drawn into intimate embraces by the relentless pull of gravity. During these encounters, stars, gas, and dark matter are stirred into a complex dance that fundamentally reshapes their structures. Sometimes, the merger of two elegant spiral galaxies results in a single, massive elliptical galaxy, losing the intricate spiral patterns of the progenitors in the process. These cosmic interactions can also compress gas clouds, igniting brilliant bursts of star formation that illuminate the darkness. This grand process unfolds over hundreds of millions of years, quietly but profoundly altering the face of the universe. Our own Milky Way is an active participant in this history, having grown by consuming smaller neighboring galaxies, leaving behind stellar streams as ghostly evidence of past conquests. Looking forward, a much larger event awaits us as the Andromeda Galaxy approaches on a collision course. In several billion years, these two giants will merge into a new, larger entity, their forms redefined through a process of destruction and rebirth. A galaxy's vitality is ultimately tied to its fuel reserves. The birth of stars depends on cold gas, and without it, the engines of creation fall silent. Over eons, galaxies either exhaust their gas through continuous star formation or lose it to the powerful outflows driven by supernovae and central supermassive black holes. When this reservoir is depleted, a galaxy enters a state of quiescence, and its stellar population begins to age and redden. These systems are sometimes called red and dead, signifying that their era of active growth has concluded. The supermassive black holes lurking at the hearts of almost every large galaxy add another layer of complexity to this story. As these giants consume gas, they release staggering amounts of energy, heating the surrounding medium and preventing it from cooling or collapsing into new stars. In this way, the central black hole can dictate when a galaxy moves into its silent, twilight years. Furthermore, galaxies inhabit even larger structures known as galaxy clusters, where the dense environment leads to more frequent interactions that strip away gas or force mergers, creating a harsh setting where many galaxies quickly become aged and gas-poor. Despite their apparent permanence, galaxies are moving toward an inevitable end. As the universe ages, the overall rate of star formation across the cosmos is declining. Galaxies dim as their stars age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. In the distant future, galaxies will no longer be lit by the brilliance of young stars but will instead resemble vast collections of stellar corpses, flickering dimly in the encroaching darkness. Every galaxy we observe today carries the marks of countless births, deaths, and collisions, an archive of light written across the night sky. Among these are the so-called dead disk galaxies, massive systems that have retained their flat, spiral shapes but have ceased forming new stars. These are the husks of magnificent machines, where the form remains but the driving energy is gone. This transition is often driven by external forces, such as ram pressure stripping in dense clusters, where the hot plasma of the cluster environment literally scrapes away a galaxy's gas, or internal feedback from a black hole that chokes off the star-forming engine from within. The visual impression of these dead disks is one of haunting beauty, with their older, cooler stars casting a dim, reddish glow. They serve as both relics of the past and omens of our own future, as the Milky Way too will eventually exhaust its gas and settle into a long silence. However, these transitions are rarely abrupt. Some galaxies linger in intermediate states for billions of years, with tiny pockets of gas still sparking the occasional new star. Modern telescopes like Hubble and James Webb allow us to peer into these fossilized systems, analyzing the ages of their stellar populations to reconstruct their long timelines of decline. These studies reveal that some galaxies finished their active lives very early in cosmic history, reminding us that even the grandest structures have a finite lifespan. Yet, even in silence, they tell a story of endurance. While new stars may no longer be born, the ancient ones will continue to shine for eons, sailing through the void as memories of a brighter age. The story of galactic mergers and decay is one of constant transformation, where the old gives way to the new, ensuring that even in the face of cosmic aging, the process of creation and change never truly halts until the very end. The silence of the universe remains one of its most profound mysteries. When we gaze at the stars, we instinctively feel that among those billions of suns, there must be others looking back at their own night sky, pondering the exact same questions. The sheer scale of the cosmos almost forces us to believe in life, with hundreds of billions of stars in our galaxy alone, many harboring their own planetary systems and trillions of other galaxies beyond. The statistical probability of intelligent life seems high. Yet, as we listen and search, we find nothing. This is the heart of the Fermi paradox. If the universe should be teeming with life, why do we hear only silence? Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" the paradox suggests that if civilizations had billions of years to rise and expand, even at modest speeds, they should have colonized the galaxy and left detectable traces long ago. We see no such signs. This implies that either intelligent life is far rarer than we imagine, or that civilizations rarely survive long enough to bridge the gaps between stars. As our understanding of exoplanets grows, the question becomes sharper. We now know that planets are ubiquitous, and many exist in the habitable zones of their stars. Life on Earth appeared almost as soon as conditions allowed, suggesting that the initial spark of life might be easy to ignite. However, the transition to advanced technology remains shrouded in absolute silence. Some argue the problem lies in our methods. For decades, projects like SETI have listened for radio signals, hoping to catch a deliberate broadcast or the accidental electromagnetic leakage of a distant society. But the radio sky remains quiet. Perhaps they use technologies we cannot yet conceive, or perhaps they have no desire to communicate. There is also the daunting reality of distance. The galaxy is so vast that signals may not have reached us yet, or may have arrived so weakened that they are indistinguishable from background noise. A conversation across 1,000 light-years takes a millennium just to send a one-way message, a timescale far exceeding a human life, or even the stability of many civilizations. This leads us to the concept of the Great Filter. Imagine the journey of life as a series of hurdles or gates. The first gate is the origin of life itself, the second is the leap to complexity and multicellularity, and the third is the development of intelligence and technology. The Great Filter is a barrier so difficult to cross that almost no one makes it through. If the filter is behind us, it means we are incredibly lucky, an anomaly in a universe of simple organisms. But if the filter lies ahead, the outlook is much darker. It suggests that civilizations reaching our level of advancement inevitably face a catastrophe that prevents them from becoming interstellar. This could be self-destruction through nuclear conflict, runaway artificial intelligence, biological warfare, or ecological collapse. Perhaps societies that fail to balance growth with the finite limits of their home planet simply burn out before they can reach the stars. The universe also presents external filters. Supernovae, gamma-ray bursts, and asteroid impacts can reset the clock on life at any time. In the galactic graveyards, the older, quieter regions of the cosmos, the environment becomes even more hostile. These areas are depleted of the gas and dust needed to forge new stars and planets. The remaining stars are often temperamental red dwarfs that lash out with sterilizing flares, or aging giants that destabilize everything in their vicinity. In these regions, the chemical cycle has slowed to a crawl, and the fresh materials required for complex biology are locked away in the husks of dead stars. Complex life requires long periods of stability and a steady supply of heavy elements, luxuries that are increasingly rare in a maturing and eventually decaying universe. The silence of the cosmos is not necessarily a sign of absence, but perhaps a reflection of fragility. It forces us to confront the possibility that we might be the first to walk the grand stage, or among the few who have survived the early hurdles. This realization acts as a mirror, showing us the vulnerability of our own light. Whether the Great Filter is a relic of our past or a shadow in our future, it challenges us to act with caution and wisdom. If we are to be the exception that survives, we must navigate the exponential risks of our own technology and the limits of our planet. The cosmic silence reminds us that while the universe is ancient and vast, the fire of intelligence is a rare and precious flame that requires extraordinary effort to keep burning in the dark. In the silent reaches of dead galaxies, the absence of new star formation means the end of continuous chemical enrichment. Over trillions of years, as stars burn out and the cosmic cycle grinds to a halt, the chemical environment becomes stagnant. Worlds rich in the heavy elements necessary for life become increasingly rare. If life ever existed in these systems, it would have to face a harsh reality of dwindling resources and a complete lack of replenishment. Some might argue that microorganisms could remain resilient under such conditions, and this is certainly possible. On Earth, we see microbes thriving in the scalding vents of the deep ocean, the frozen deserts of Antarctica, and even within radioactive waste. Similar forms of life might persist in the subsurface oceans of moons or deep within the rocky crusts of planets orbiting ancient stars, shielded from the hostile surface. However, the probability that such life could evolve into a complex ecosystem capable of developing intelligence and building civilizations drops precipitously. Complex life requires more than just mere survival. It demands stability over immense time scales, consistent energy sources, and protection from catastrophic radiation, all of which are in short supply within a galactic graveyard. Perhaps the universe has an inherent limit on the life it can sustain. The very conditions that allow galaxies to form and evolve also dictate their eventual descent into habitability. There may be a golden age for every galaxy, a specific window of time where life can spark and flourish. But as the galaxy exhausts its fuel, that window begins to close. This could explain why we have yet to detect other civilizations. Their lifespans may be inextricably linked to the relatively short active phases of their host galaxies. By the time we look toward them, their suns may already be taking their final bow. On Earth, it took billions of years for complex life to emerge and even longer for intelligence to arrive. If a planet were placed in a galaxy already nearing its end, the era of steady starlight might not last long enough for intelligence to evolve before the lights go out and resources vanish. This suggests that complex life depends not just on the right planet or the right star, but on the right epoch of cosmic time. Too early, and the universe lacks the heavy elements to build terrestrial worlds. Too late, and the energy required for growth is gone. The grand narrative of life may not be spread evenly across the cosmos but tied to specific eras. Outside these windows, the universe is simply too harsh, too unstable, or too depleted. We are fortunate to live in a galaxy like the Milky Way, which is still actively forming stars, and to orbit a sun stable enough to provide billions of years of warmth on a planet with the perfect chemical balance. We may find ourselves in a rare, privileged moment of cosmic history. The silence of the universe does not necessarily mean that life is impossible. It may simply mean that the window for life is incredibly narrow, and most of the universe has already passed through it. That concludes our exploration for today. I hope these insights accompany you into a peaceful rest and inspire a wonderful day ahead. Thank you for joining us on this journey through the stars. Until next time.